capacitor is called a displacement current. Tesla coil discharges are formed as a result of displacement currents as pulses of electrical charge are rapidly transferred between the high-voltage toroid and nearby regions within the air, called space charge regions. Although the space charge regions around the toroid are invisible, they play a profound role in the appearance and location of Tesla coil discharges. When the spark gap fires, the charged capacitor discharges into the primary winding, causing the primary circuit to oscillate. The oscillating primary current creates an oscillating magnetic field that couples to the secondary winding, transferring energy into the secondary side of the transformer and causing it to oscillate with the toroid capacitance to ground. Energy transfer occurs over a number of cycles, until most of the energy that was originally in the primary side is transferred to the secondary side. The greater the magnetic. A small, later type Tesla coil in operation, the output is giving 43 cm, 17 in, sparks. The diameter of the secondary is 8 cm, 3.1 in. The power source is a 10000 V, 60 Hz current limited supply. Coupling between windings, the shorter the time required to complete the energy transfer. As energy builds within the oscillating secondary circuit, the amplitude of the toroid's RF voltage rapidly increases, and the air surrounding the toroid begins to undergo dielectric breakdown, forming a corona discharge. As the secondary coil's energy and output voltage continue to increase, larger pulses of displacement current further ionize and heat the air at the point of initial breakdown. This forms a very electrically conductive route of hotter plasma, called a leader, that projects outward from the toroid. The plasma within the leader is considerably hotter than a corona discharge, and is considerably more conductive. In fact, its properties are similar to an electric arc. The leader tapers and branches into thousands of thinner, cooler, hair-like discharges, called streamers. The streamers look like a bluish haze at the ends of the more luminous leaders. The streamers transfer charge between the leaders and toroid to nearby space charge regions. The displacement currents from countless streamers all feed into the leader, helping to keep it hot and electrically conductive. The primary break rate of sparking Tesla coils is slow compared to the resonant frequency of the resonator top-load assembly. When the switch closes, energy is transferred from the primary LC circuit to the resonator, where the voltage rings up over a short period of time, culminating in the electrical discharge. In a spark-gap Tesla coil, the primary to secondary energy transfer process happens repetitively at typical pulsing rates of 5500 times per second, depending on the frequency of the input line voltage. At these rates, previously formed leader channels do not get a chance to fully cool down between pulses. So, on successive pulses, newer discharges can build upon the hot pathways left by their predecessors. This causes incremental growth of the leader from one pulse to the next, lengthening the entire discharge on each successive pulse. Repetitive pulsing causes the discharges to grow until the average energy available from the Tesla coil during each pulse balances the average energy being lost in the discharges, mostly as heat. At this point, dynamic equilibrium is reached, and the discharges have reached their maximum length for the Tesla coil's output power level. The unique combination of a rising high-voltage radio frequency envelope and repetitive pulsing seem to be ideally suited to creating long, branching discharges that are considerably longer than would be otherwise expected by output voltage considerations alone. High-voltage, low-energy discharges create filamentary multibranch discharges which are purplish-blue in color. High-voltage, high-energy discharges create thicker discharges with fewer branches, are pale and luminous, almost white, and are much longer than low-energy discharges, because of increased ionization. A strong smell of ozone and nitrogen oxides will occur in the area. The important factors for maximum discharge length appear to be voltage, energy, and still air of low to moderate humidity. There are comparatively few scientific studies about the initiation and growth of pulsed lower frequency aft discharges, so some aspects of Tesla coil air discharges are not as well understood when compared to DC power frequency AC, HV impulse, and lightning discharges. Applications. Today, although small Tesla coils are used as leak detectors in scientific high vacuum systems, and igniters in arc welders, 47, their main use is entertainment and educational displays. Education and entertainment. Electrum sculpture, the world's largest Tesla coil. Builder Eric Orr is visible sitting inside the hollow spherical high-voltage electrode. Tesla coils are displayed as attractions at science museums and electronics fairs, and are used to demonstrate principles of high-frequency electricity in science classes in schools and colleges. 48. Since they are simple enough for an amateur to make, Tesla coils are a popular student science fair project, and are homemade by a large worldwide community of hobbyists. Builders of Tesla coils as a hobby are called coilers. They attend coiling conventions where they display their homemade Tesla coils and other high-voltage devices. Low-power Tesla coils are also sometimes used as a high-voltage source for Coilian photography. The current world's largest Tesla coil is a 130,000 watt unit built by Greg Lee and Eric Orr, part of a 38-foot-tall, 12 m sculpture titled Electrum owned by Alan Gibbs and currently residing in a private sculpture park at Kakanua Point near Auckland, New Zealand. 49, 50. Another very large Tesla coil, designed and built by Sid Klinge, is shown every year at the Coachella Valley Music and Arts Festival in Coachella, California. Tesla coils can also be used to generate sounds, including music, by modulating the system's effective break rate, i.e., the rate and duration of high-power RF bursts, via MIDI data and a control unit. The actual MIDI data is interpreted by a microcontroller which converts the MIDI data into a PWM output which can be sent to the Tesla coil via a fiber optic interface. An extensive outdoor musical concert has demonstrated using Tesla coils during the Engineering Open House, EOH, at the University of Illinois Urbana-Champaign. The Icelandic artist Björk used a Tesla coil in her song Thunderbolt as the main instrument in the song. The musical group Arc Attack uses modulated Tesla coils and a man in a chain-link suit to play music. Vacuum system leak detectors. Scientists working with high vacuum systems test for the presence of tiny pinholes in the apparatus, especially a newly blown piece of glassware, using high-voltage discharges produced by a small handheld Tesla coil. When the system is evacuated, the high-voltage electrode of the coil is played over the outside-off apparatus. At low pressures, air is more easily ionized and thus conducts electricity better than atmospheric pressure air. Therefore, the discharge travels through any pinhole immediately below it, producing a corona discharge inside the evacuated space which illuminates the hole, indicating points that need to be annulled or reblown before they can be used in an experiment. Tesla forces. In 2016, Rice University scientists used the field of a Tesla coil to remotely align tiny carbon nanotubes into a circuit, a process they dubbed Tesla forces. 51, 52, health issues. The high-voltage radio frequency, RF, discharges from the output terminal of a Tesla coil pose a unique hazard not found in other high-voltage equipment. When passed through the body, they often do not cause a painful sensation and muscle contraction of electric shock, as lower frequency AC or DC currents do. 53, 8, 54, 55. The nervous system is insensitive to currents with frequencies over 1020 kHz. 56. It is doubt that the reason for this is that a certain minimum number of ions must be driven across a nerve cells. Boy allowing arc from Tesla coil to strike hand. He feels no pain membrane by the imposed voltage to trigger the nerve cell to depolarize and transmit an impulse. At radio frequencies, there is insufficient time during a half cycle for enough ions to cross the membrane before the alternating voltage reverses. 56. The danger is that since no pain is felt, experimenters often assume the currents are harmless. Teachers and hobbyists demonstrating small Tesla coils often impress their audience by touching the high voltage terminal or allowing the streamer arcs to pass through their body. 57, 58, 8. If the arcs from the high voltage terminal strike the bare skin, they can cause deep-seated burns called RF burns. 59, 60. This is often avoided by allowing the arcs to strike a piece of metal held in the hand, or a thimble on a finger, instead. The current passes from the metal into the person's hand through a wide enough surface area to avoid causing burns. 8. Often no sensation is felt, or just a warmth tingling. However, this does not mean the current is harmless. 61. Even a small Tesla coil produces many times the electrical energy necessary to stop the heart, if the frequency happens to be low enough to cause ventricular fibrillation. 62, 63. A minor misadjustment of the coil could result in electrocution. In addition, the RF current heats the tissues it passes through. Carefully controlled Tesla coil currents, applied directly to the skin by electrodes, were used in the early 20th century for deep body tissue heating in the medical field of long-wave diadermy. 54. The amount of heating depends on the current density, which depends on the power output of the Tesla coil and the cross-sectional area of the path the current takes through the body to ground. 55. Particularly if it passes through narrow structures such as blood vessels or joints, it may raise the local tissue temperature to hypothermic levels, cooking internal organs or causing other injuries. International IGNERP safety standards for RF current in the body in the Tesla coil frequency range of 0.11 MHz specify a maximum current density of 0.2 mA per square centimeter and a maximum power absorption rate, SAR, in tissue of 4 W/kg in limbs and 0.8 W/kg average over the body. 64. Even low-power Tesla coils could exceed these limits, and it is generally impossible to determine the threshold current where bodily injury begins. Being struck by arcs from a high power, and GT 1000 watt, Tesla coil is likely to be fatal. Another reported hazard of this practice is that arcs from the high voltage terminal often strike the primary winding of the coil. 53, 61. This momentarily creates a conductive path for the lethal 50 or 60 Hz primary current from the supply transformer to reach the output terminal. If a person is connected to the output terminal at the time, either by touching it or allowing arcs from the terminal to strike the person's body, the high primary current could pass through the conductive ionized air path, through the body to ground, causing electrocution. Skin effect myth. An erroneous explanation for the absence of electric shock that has persisted among Tesla coil hobbyists is that the high-frequency currents travel through the body close to the surface, and thus do not penetrate to vital organs or nerves, due to an electromagnetic phenomenon called skin effect. 62, 8, 65, 66. This theory is false. 67, 68, 69, 53. 63, 70. RF current does tend to flow on the surface of conductors due to skin effect, but the depth to which it penetrates, called skin depth, depends on the resistivity and permeability of the material as well as the frequency. 71, 72. Although skin effect limits currents of Tesla coil frequencies to the outer fraction of a millimeter in metal conductors, the skin depth of the current in body tissue is much deeper due to its higher resistivity. The depth of penetration of currents of Tesla frequency, 0.11 MHz, in human tissues is roughly 2472 centimeters, 928 inches. 72, 71, 53. Since even the deepest tissues are closer than this to the surface, skin effect has little influence on the path of the current through the body. Winking sad smiley 70. It tends to take the path of minimum electrical impedance to ground, and can easily pass through the core of the body. 73.